Yes.
A pool ball leaves a 0.6 meter high table with an initial horizontal velocity of 2.4 meters a second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's location. Okay, so what we have here is clear x-axis, clear y-axis. Our y-axis being the pool table right here is 0.6 meters high, and then the x-axis being the floor. We don't know the distance, it's one of the things that we're looking for. We do know that it left with a 2.4 meters a second velocity x direction, in the x direction. So what we do is we break it down into what we know for x and y axis. The x-axis info, we don't know what his final x was. That's what we're looking for. The initial x velocity was 2.4 meters a second, meaning that's how fast it left the table. The acceleration for x in the x direction is 0. We know that it hits right here, no more acceleration. Okay? So now the y info. We know that that pool table is 0.6 meters high. That is our y right here. Our y initial velocity is going to be 0. There is no velocity acting in the y direction, so it's 0. So our acceleration, on the other hand, for the y direction is gravity, negative 9.8 meters a second squared, so meters per second per second. All right, our basic equation for this comes down to distance, velocity initial times time, plus 1/2 acceleration times time squared. That being the case, what do we have that we can put into our equation, or what do we have that we can help our equation solve for, that we can get one of our two factors, either distance or time? Well, the x-axis, we don't really have anything. We have the initial velocity, and then we have the acceleration. If you look at our equation, that doesn't get us anywhere. Acceleration, that'd be 0. Initial velocity, 2.4 times time. Well, we get stuck right there. We don't have time. Once again, we don't have time. So we don't have time there. Our y-axis info, we have 0.6 meters, 0 meters a second, 9.8 meters a second. We have 3 factors, so it'll be much, much easier to use those to solve for our last remaining factor, which is going to be time. So if we start moving things around, we see that we plug in our velocity initial on the y-axis, turns out to be 0. So basically it nullifies that first whole half of the equation, of our equation. So we end up with y 1/2 at squared, which is good. It's simple. It's much easier that way. So from here, we can do two things. We can either solve for x, which is mapped out here, or we can use this equation. So t equals the square root of y divided by 0.5 times our acceleration, which is the same thing as 1/2 times acceleration. Both of them come out the same way. I've worked them out mathematically. They come out the same way, but we'll follow here. So we got 0.60, 1/2 times negative 9.8 meters a second times t squared. We go ahead and multiply times 1/2, and we get negative 0.49 equals t squared. So come down here, divide by 0.49, t squared. Take the square root of what we get from here. Eventually speaking, we end up with t equals 0.3499. That's our time. So now we know how long it took that ball and this arc to fall to this point. Now we can get this point if we use our x-axis information and we plug it in, which we do right back here. 2.4, and then 0.3499, 1/2 times 0, because that was our acceleration right there. So that nullifies the whole first part of that equation. 3.3499 times 2.4 is going to equal 0.8398. Now 2.4 was our acceleration. That's how fast it left the table. 0.349 was how long it took to hit the ground. This is how far away it hit the ground. 0.8398 meters.